Hi, my name is Yu Yang, and I am a PhD student at University of California, Los Angeles. I am very happy to present our work on explaining deep convolutional neural networks via latent visual semantic filter attention. Deep neural networks have become the go-to solution when people want to learn from a large amount of data to make predictions. It seems now that a deep neural network is all we need. Or is it? Predecessor models like linear regression make predictions based on explicitly predefined features. Thus, these models are interpretable by definition. On the contrary, deep neural networks learn features implicitly. As a result, we call deep neural networks as black box models because we cannot understand the cause of their decisions. Are they using fair and reliable features to make their decisions? We don't know, but we have to find out to make sure these models are not impacting our society negatively. So, a deep neural network is not all we need. We also need to know what it has learned from the data. In this paper, we study one type of deep neural network, deep convolutional neural network, or deep CNN for short. We consider each convolutional filters as a neuron. Given a trained deep CNN, if we can know the features learned by each convolutional filter, we can then turn this initially black box model into an interpretable one. We propose Vadis, a latent visual semantic explainer for deep convolutional neural networks. For each convolutional filter of a trained deep convolutional neural network, Vadis can provide both visual and semantic explanations for the feature learned by this filter. We designed two key components for Vadis. The first key component is latent visual semantic mapping. We learn a mapping function whose source domain is the latent visual feature representation space of the trained model, and the target domain is a well-learned semantic space. This mapping function is trained contrastively so that each visual representation is mapped closer to the related semantics and farther from unrelated semantics. With this mapping function and the learned semantic space, Vadis is able to find the most accurate explanations for any given filter, even if the concept is not labeled for the image dataset. The second key component is filter attention. It allows us to more accurately explain features that are distributed over multiple convolutional filters. When Vadis is explaining one of the filters, and we call this filter the target filter, it assigns weights to all the other filters based on how similar their activations are to the target filter's activation. The weighted combination of all filters is then used to explain the target filter. While existing work either cannot provide explicit semantic explanations or is restricted to explaining with only labels in the training data, Vadis can provide both visualization and semantic explanations with both annotated and zero-shot concepts. Plus, Vadis can provide more accurate explanations with the help of filter attention. We show with our extensive experiments that Vadis can find zero-shot concepts to give more accurate and comprehensive explanations than using only the annotated labels. Here, words in red are concepts that are not used for training Vadis. However, Vadis can still discover these more accurate words with the two proposed key components. Please check out our paper to see more details and results. Thank you.